Hello, my chemistry friends. Welcome to day 5 of remote learning. Hopefully you finished your Unit 6 test. Today we are starting Chemistry Unit 7. This is going to be a pretty short unit. It's called Kinetics and Equilibrium. Here is an overview of what our unit will look like at least through next week. We'll be doing 2 labs. We'll be doing one today, in fact, and then next week we'll be doing one that you've all been waiting for when we learn about something called catalysts. So your learning target for today, I can use collision theory to accurately predict how a change in temperature or other factors will impact the rate of a chemical reaction. That will make more sense once we learn what collision theory is today. Your to-do list, hopefully you've already finished your warm-up for today. You're doing your Edpuzzle now. It's going to be a pretty short one because the bulk of your lesson today is going to be doing a lab. We'll talk more about how that's going to work later, and then you'll end with an exit ticket today. So in general, our unit is called Kinetics and Equilibrium. It'll be splitting up into 2 parts. The first part will be kinetics. The second part will be equilibrium. Kinetics in general talks about how fast or how slow a chemical reaction will occur and the energy that's associated with it. So in your exit ticket after your Unit 6 test, I asked for a few examples about what comes to your mind when you think of a fast reaction versus a slow reaction. So I got a lot of common ones, but here are some ones that I found some gifts for. We saw at the beginning of the year when we learned about the group 1 metals, when they touch water, they immediately explode, some of them faster than others, such as cesium here. A reaction that one of your classmates has really wanted me to show you is the gummy bear and magnesium reaction. Here's Big Head, by the way, saying hi. Basically, if you take a gummy bear, which is made out of sugars, and you put it in liquid or molten potassium, this is what happens. The second it touches, it explodes and releases a lot of energy. So these are 2 reactions that visibly release a lot of energy. They don't always do that, but they happen the second that the 2 reactants touch. Now that's not always the case. There are also some slow reactions. One that I heard a little bit on your exit ticket was when food goes bad. If you're storing food in your refrigerator, refrigerator is a key thing, the food will not go bad that quickly, but eventually bacteria, decomposers come down and break it down, turn it into something new. And the most common example I saw of a slow reaction is rusting, which is taking a metal and reacting it with oxygen. We'll talk a lot more about that in the next few months. So hopefully you can see here, and hopefully through your experience in day-to-day life, you know that there are some reactions that go fast, some that go slow, and that's kind of the bulk of what we'll be learning about in this unit. One of the main things we'll be doing are talking about what are called potential energy diagrams, which are these little curved graphs. Okay, and so as you can see here, it's like we're doing a 2-step reaction. To get A and B together, it takes a lot of energy to go up this hill, and then to make it react with C at the end, it's a little bit of energy. And so we'll be drawing these diagrams, they're called potential energy diagrams, to show the relative rate of chemical reactions as they occur. So we're going to watch a little bit of a video and learn about what is called collision theory. You see the bulk of it right here in the screen.
Here's a beaker of cold water and a beaker of hot water. When you add sugar cubes to them, the one in the hot water will dissolve faster than the one in the cold water. To explain the different rates of reactions, Max Trotz and William Lewis came up with collision theory in the early 1900s. The first assumption of collision theory is that the particles must collide with one another in order to react. Most particles will act like billiard balls in a game of pool, and when they collide, they bounce off each other. The collision itself isn't all that's needed for a reaction to occur. The particles also need to have enough energy, enough speed, to break and form new bonds when they collide. The minimum energy required for a reaction to occur is called the activation energy. Some reactions require very little, and some need a lot more to get started. Generally speaking, most reactions will occur faster when the temperature is increased, because temperature is the average kinetic energy of the particles. With more kinetic energy, they will be more likely to have enough activation energy for the reaction to occur. But for some reactions, there is still one more factor: orientation. Even if the particles collide with sufficient speed, if they aren't at the correct angle, a reaction won't happen. In this example of nitrogen monoxide and ozone, the reaction didn't occur because the oxygen of each molecule touched during the collision. In this collision of the same two molecules, the nitrogen touches an oxygen and the reaction occurs, making oxygen and nitrogen dioxide. The orientation was correct, so the reaction could occur. So in summary, the three key ideas of collision theory are that particles must collide to react, they must have sufficient energy to break and make new bonds, and they must collide with the correct orientation.
Alright, so hopefully that video gave you a quick summary. I'll have this video and a few other lengthier ones that explain collision theory attached on the Google Classroom post. But collision theory is this idea that in order for a chemical reaction to occur, which means to break or to form bonds, you have to have particles actually physically bump into each other. And not only are they going to bump into each other, they have to do it with enough energy, meaning they have to hit hard enough. And as you saw in that last example, they have to hit in the correct orientation or position. This is important because if your atoms that want to bond to each other don't touch, there's no way that they're going to end up bonding to each other because they're not near each other. An example of what I like to think of this is if you're trying to hit a home run in baseball. You're going to hit it as hard as you can, and you have to hit it in the right spot. Otherwise, you're not going to achieve your goal. And so what we're going to be talking about is how we can make a reaction go faster or go slower by changing the amount of effective collisions that occur. Okay, and so if particles are colliding more often and there are more effective collisions, then your reaction will happen faster. If there are less collisions, your reaction will happen slower. So I want to ask you a question. Based on what you already know about chemistry and what you just learned about collision theory, what do you think will happen to the number of effective collisions if you increase the temperature of a system, and why? Another way you can phrase this is if the temperature is blank, then the rate of the reaction will blank. Hopefully in the last one you said as we increase the temperature, the reaction will go faster. And the reason for that is because there will be more effective collisions. If you look in my lovely little GIFs here, you can see the one that is hotter or at a higher temperature. It means the particles are moving faster. If the particles are moving faster, they're one, more likely to bump into each other, and two, they're going to hit each other with more energy and more force, meaning that the probability of having an effective collision will increase. This will make the reaction go faster. If you're on the PowerPoint slides when you're studying later, this is a link to another website where you can further explore this, and I'll attach it during our materials on Google Classroom. So the Regents identifies 6 things that they want you to know. 1, that you can change them to change the rate of a chemical reaction, but they also want you to predict like we just did. If we increase one of these, then the reaction will go blank, faster or slower. Today we'll be doing a lab. We'll be focusing on changing temperature, and we'll be looking at surface area. But these other ones, you'll be getting a reading attached to this probably on Friday that kind of explains it, but we'll be going through them in detail over the course of this unit. So this video here, I'm not going to play. I have it attached with your preview video on your exit ticket after Unit 6 test, but it kind of gives you an idea and a pretty funny metaphor for how you can make a reaction go faster by changing one or more of those 6 properties. Okay. So for today, your lab, we're going to be looking at 2 things. We're going to be doing a reaction that we did in our very last lab, which is putting Alka-Seltzer in water. We know that this is a chemical reaction because of the gas bubbles that are produced. Those are carbon dioxide. You're going to learn a little bit more about them on your pre-lab for today. But we're going to see if we can make this reaction happen faster or slower by changing things like the temperature of the water and also changing the surface area. So here you can see we have one full tablet broken into smaller pieces and then ultimately crushed here at the end. This is a lab that if you happen to have these materials at home, meaning just an Alka-Seltzer, different temperature water, and some cups or some beakers, you can actually do it on your own, or I'm going to have videos for each of the different variable changes for our lab today. Okay, before I let you guys go, I do want to give a little FYI about surface area because it historically has been something that's confusing. Temperature, everybody's clear with. When it's hot water, it's an increase in temperature. When it's cold water, it's a decrease. But surface area, we're going to be taking the Alka-Seltzer and breaking it apart into smaller pieces. Now, do you think this is an increase in surface area or a decrease? This picture here shows you the 1 cube, and that can be like one piece of Alka-Seltzer. When it's reacting with the water, it only reacts here, here, and here, and then the other faces that you can't see. But when we break it apart into smaller pieces, do you see all these other faces that are free? Those are places where water can collide with the Alka-Seltzer. And if it collides more, then the reaction will go. You'll find out in your lab today. Okay, another way you could think of that is bread. Here is bread that is not sliced. I can only put butter here and here. It's not going to work out, but as you slice it, you increase the amount of surfaces where you can add butter to your bread. Okay, so next on your to-do list is going to be answering a couple of questions. They're going to be pretty short, multiple choice ones today, and then you're going to do your lab. Your lab may take you a little while. If you have questions or if you want to go through it, I have office hours this week from 11 to 2 for the rest of the week, and then you will have an exit ticket. Friday is pretty much just going to be a work day this week, and so your lab will be due on Monday or Tuesday of next week, but please keep in mind that you will be getting an additional shorter assignment to do on Friday. Okay, thank you. Have a good day.